Hi, this is Algebra 1, Lesson 97. We're going to talk about angles and triangles, the Pythagorean Theorem, and Pythagorean Triples. We're starting on page 405. So, starting with angles and triangles, here we have two intersecting lines. The lines intersect at this point, and because the lines intersect, we are left with four angles. We have angle A, which goes from here to here. We have angle B, which goes from here to here. We have angle C, which goes from here to here. And we have angle D, which goes from here to here. Right? There's some nice math theory on page 406 and 407 that help you understand how an angle is defined, mathematically speaking. Read it. It's very interesting. Actually, it's interesting to know that different people define angles differently. Math is a funny thing. For now, you need to know that these are angles, right? Okay. So, an angle is formed by two rays that are in the same plane and have a common endpoint. So, a little bit of math background. This is a line, right? A line travels across points. It has no beginning and no end. It just continues, right? A ray is sometimes also called a half line. So a ray has an endpoint, and then from the endpoint it travels in one direction through points on the same plane. So this is a ray. And from the same endpoint, this is a ray. And these two rays that meet at the same endpoint share this angle, make this angle. Okay? Here's a little bit more review. If two straight lines are perpendicular to each other, so they meet at a right angle, right? The measure of their four angles is 90 degrees. So if our angles went like this across these lines, and if I could draw straight lines, these would all be right angles. And the measure of each of these angles would be 90 degrees, correct? The sum of the interior angles of any triangle is 180 degrees. So on page 406, at the bottom of the page, okay, we have a picture of three triangles. This one is a right triangle. We know that because they put a little square in the corner. This is a 60-degree angle, and this is a 30-degree angle. So 60 plus 30 is 90, plus 90 is 180, right? Here's an equilateral triangle, which means all of the sides have the same measure and all of the interior angles have the same measure. The interior angles of an equilateral triangle are always 60, 60, and 60. Because they're always going to add up to 180, and if the sides are equal, then the angles are equal. So 180 divided by 3 is 60. Here's an obtuse triangle, and its measurements are 135 in the obtuse angle, 25 degrees here, and 20 degrees here. And if we added these up, they would equal 180 degrees. Okay? A 90-degree angle is called a right angle, and any triangle that contains a right angle is called a right triangle. So this is a right triangle. In every right triangle, the side opposite the right angle is the longest side, and we call that side the hypotenuse. Hypo means under, and tenon means to stretch. So hypotenuse means to stretch under. So here's a right triangle. These sides we sometimes call legs. So these could be the legs of a right triangle or the sides, either way. And the longest side, which is always opposite the right angle, is called the hypotenuse. Okay, farther down on page 407, we have this definition of the Pythagorean Theorem. So it can be shown that squares drawn on the hypotenuse of a right triangle has the same area, the square drawn right here. So this square has the same area as the sum of the areas of the squares drawn on the other two sides. Okay, so here we have a right triangle in the center here. Okay? They took the measurement of the sides and they made a square off of each of these angles. So this side is 3 units. So they made an area, a square that's 3 units by 3 units. That means the area of this square is 9, right? 3 times 3. Okay, this side measures 4 units. So its square is 4 times 4. This side measures 5. So its square is 5 times 5, which is 25. The point of this Pythagorean theorem is that the area of this square, which was 9, plus the area of this square, which was 16, equals the area of this square, 25. 9 plus 16 equals 25. Okay? While this theorem was known to the Egyptians as early as the Middle Kingdom, about 2000 BC, the geometric proof of the theorem is normally attributed to a Greek philosopher and mathematician called Pythagoras. Pythagoras was born on the Aegean island of Samos and was later associated with a school or brotherhood in the town Crotona on the Italian peninsula in the 6th century BC. We call the theorem for which he supposedly developed the proof the Pythagorean Theorem. Okay? So the general algebraic expression of the Pythagorean theorem, back up here, is a squared plus b squared equals c squared, where a and b are legs of a right triangle and c is the hypotenuse. Okay? The sun is following me. I keep moving the table to try to get away from it. Okay, so here's an example. Given the triangle with the lengths of the sides shown, use the Pythagorean theorem to find A. Okay, so we have a leg that's 4, we have a leg that's A, and we have the hypotenuse that measures 5 units. So we're going to use the Pythagorean theorem to solve for A. The Pythagorean theorem says that a squared plus b squared equals c squared. So, let's see if that will block out some light. Woohoo! So we could say that a squared plus 4 squared is going to equal 5 squared. Okay? We can move this 4 squared over to this side. And we have a squared equals 5 squared minus 4 squared, which equals 25 minus 16, which equals 9. So a squared equals 9. This is the side of a triangle, so it's not going to be measured in a negative. So we are not going to use a plus or minus when we take the square root of both sides. So we have a equals the square root of 9, which is 3. So a equals 3. Okay, here's another triangle. Okay, it says find side P. So here's the right angle. We know that the side opposite is the hypotenuse, so in this case P is the hypotenuse. So we have a squared plus b squared equals c squared. It doesn't matter which of the legs is a and which one is b. because it's added. So it doesn't matter which order they're in. So we're going to say 4 squared plus 5 squared equals p squared, because that's the hypotenuse for us this time. So 16 plus 25 equals p squared. 16 plus 25 is 41 equals p squared. To solve for p, we're going to take the square root of both sides. So the square root of p squared is p, and the square root of 41 is the square root of 41. It's not going to be plus or minus because these are measurements, so they're not going to be negative. Okay, so your answer is going to be p equals the square root of 41, and there's nothing else you can do to simplify that. Okay, here's another one. Find k. Here's the right triangle. So this side is the hypotenuse. So k is one of the legs. So we can say that k squared plus 5 squared equals the square root of 61 squared, right? Okay, so we have k squared equals the square root of 61 squared is going to be 61. Minus, okay, let's subtract the 5 squared from both sides. So minus 25. 61 minus 25 is 36. So k squared equals 36. Now we can take the square root of both sides. So k equals 6. And that's our answer. Let's try another one. Find the side M. So here's our triangle. Not very well drawn. Here's the right angle. So the M side is the hypotenuse this time. It's the side opposite the right angle. So we have M squared equals 8 squared plus 12 squared, which equals 64 plus 144, which equals 208. Okay, so M squared equals 208. So M is going to equal the square root of 208. And if we find all of the roots of 208, this is going to equal 4 times the square root of 13. It's ugly, but it's correct. They're not always going to come out with pretty answers. Okay, now we're going to talk about Pythagorean triples. You can save yourself some time and trouble if you learn to recognize certain right triangles. We named the triangles by the lengths of their sides in ascending order. So, in ascending order, which means we start with the shortest side and we work our way up, this is a 3, 4, 5 right triangle. This one would be a 5, 12, 13 right triangle. Here we have an 8, 15, and 17 right triangle. Okay? If you see right triangles with a 3 and a 4, you know this one's going to be a 5. Or a 3 and a 5, you know this one's going to be a 4. Okay? So these are good ones to memorize. It's useful to know that any multiple of a Pythagorean triple is also a Pythagorean triple. So if we have a 3, 4, 5 triangle, then if this side is 6 and this side is 8, because these two are multiples, this one's going to be 10. Okay? Because 3 times 2 is 6, 4 times 2 is 8, so 5 times 2 is going to be 10. In the same way, if we multiply this one by 3, we get a 9, 12, and 15 triangle. So, here are some examples. Recall the appropriate Pythagorean triple to find the unknown length in each of the following right triangles. So we have A, 5, and 12. And if you look back into your book, you will remember that we have a 5, 12, 13 Pythagorean triple. So this is going to be a 5, 12, 13 right triangle. Okay? Now we have an 8, a B, and a 17. So if we look back, we can remember that this is going to be an 8, 15, and 17 right triangle. Okay? Oh, sorry. So A is going to equal 13, and B is going to equal 15. Okay, here we have 8 and 10, and we can recognize that 8 divided by 2 is 4, and 10 divided by 2 is 5, and therefore this one is going to be a multiple of 3. So we have a 3, 4, 5 triangle. In this case, both of these two are multiplied by 2, so this is also going to be multiplied by 2, and 3 times 2 is 6. And this is a 3, 4, 5 right triangle that has been multiplied by 2, by a factor of 2. Okay, that is it for this lesson. Basically a review and recognizing some Pythagorean triples. All right, try the practice problems. Let me know if you have any questions, and do your homework. Thank you.